Okay, we're not rolling. And I'll put this in the chat too. All you got to do is, so this one's 6 minutes. We're going to cover forecasting here.
Hi, welcome to this series of videos on mechanics of forecasting methods. I am Piyush. We will talk about seasonal indices. The series is about 5 specific items: the moving average, the exponential smoothing, trend line, seasonal indices, to be followed by measures of forecasting accuracy. There will be some support videos in addition to these 5 main videos to help you understand the methods better.
Cover the
The
first
seasonal
3 in the
indices
basic.
that we are talking about here is a very simple version, suitable only for seasonal variation. In case the data has a combination, say random and seasonal or trend and seasonality, this particular method would not be suitable. And as always, these quantitative methods are generally suitable for short term and in some cases for medium term. Let's jump into the data. The data set that we have here is to be first plotted so that we can understand the type of variation. We take a line chart and it clearly tells us that there is a seasonality in action, where if you look at the table here, every second quarter there's a peak: 185, 190 and 188. This is the second quarter. And every fourth quarter, 94, 90 and 95, there's a dip. So clearly season variation in play. Now let me show the table which we already have here. It's just replotted. So there are 4 years, 3 years here, year 1, year 2 and year 3, and 4 quarters. Those are the seasons. The seasons need not be 4 quarters. They can be each day of the week. They can be every hour in case of McDonald's. Alright, so what we do here is first find the total sale of every year, and each year equal to sum this data. Control C, enter. These are the total of each of the years, and we also find the average per quarter. So equal to average of each of these 4 data sets. Wonderful. Control C. Now what this says is in the first year the total sale was 556, and in absence of seasonality the sale per quarter would have been 139 units. Same thing for year 2, it's 555, and in absence of seasonality it would have been 138.75 per quarter. I'll copy this template here to help me indices, and I'll just delete the data. So the seasonal index for the first quarter would be the demand of that particular quarter, which is 145, divided by the average. The average, remember, represents the demand had there been no seasons. So this division tells us that the effect of seasonality is to increase the sale by 4%. 1.04 represents 4.3% here. We fix up the 8th row so that the formula can be copied, and we get the seasonal index for every quarter of that first year. So for the fourth, which is the dip, the worst quarter, we say that the seasonality brings down the average sale by around 32.4%. We can again copy this for the remaining 2 years to give us 3 values of seasonal index for each quarter. I can sum them up and average. I can take the median. I can omit the maximum and the minimum. There are many ways to get to one number of the seasonal indices. Here we'll take the average of these 3 methods. Control C and paste it down. A technical point: the sum of these seasonal indices should equal to the number of periods of the year or the day that we are considering. So since we have 4 quarters, the sum should be 4, equal to sum of these 4 periods. Wonderful, it is 4. In case it is not, we would have to proportionately increase or decrease each of the seasonal indices to make it equal to 4. So now these are the seasonal indices for each of the 4 quarters. In case somebody tells me that there is a year 4, um, year 4 with a total demand expected to be around 570. So the average uh, of every quarter would be around 570 divided by 4, which is 142.5. For the year 4, 1 to year 4, and each of the quarter 1, quarter 2, quarter 3, and quarter 4, this forecast for year 4 quarter 1 would be equal to average multiplied by equals to average. Let me do it again. Multiplied by the seasonal indice of that quarter. So it's 142, which is the average without the season, multiplied by 1.03 to put in the effect of the season. F2, let me fix up the 19th row and then copy this to get me the forecast for each and every quarter of the next year. So this is how to calculate the seasonal indices and use the seasonal indices for forecasting the future. Thank you for watching the video. Please like it if it helped you, share it and communicate it about it to your friends. In case.
All right, so that's seasonality with our buddy Piyush. Now, we'll go look at forecast accuracy with Piyush. This is like 7 minutes.
Hi, welcome back to this video series on mechanics of forecasting methods. I am Piyush. The series had 5 videos or 5 series on moving averages, exponential smoothing, trend lines, seasonal indices. This last one on measures of forecasting accuracy. There also have been support videos on how to use each of these methods better. Forecasting accuracy, there are 3 basic purposes of why we measure. 1, to check the performance of how we are doing. 2nd, to recalibrate. So for example, if we have selected certain methods, certain values of alpha or gammas or seasonal indices, we need to check if those values are relevant. And 3, if we are selecting a forecasting method, we would want to compare across various forecasting methods, which does a good job. So sometimes to compare, use measures of accuracy. In this video, we will only see 4 specific methods: a bias, mean absolute deviation or MAD, mean absolute percentage error or MAPE, and tracking signal. There are many other methods, but we limit ourselves to these 4. Now the data set, we have 12 periods of data, the actual demand and the forecast. The first is the error, which is the easiest. Now the error is nothing but the actual minus the forecast. Having selected this, I just drag it. So these are the errors of each and every period, and the summation of these errors, the average of these errors is what we call as bias. Bias is the average of these errors. So I say equal to, I beg your pardon, equal to average of all these numbers here. Bracket close, enter, gives me bias. So in this case, our bias is very close to 0, a negative 0.167. The running sum of forecast errors, RSFE, the running sum, is the continuous summation of the errors. So since we are starting here, this would be equal to the minus 2. For the next period, it is minus 2 plus 8. And the next period would be 6 plus 7. So I can drag it to get the running sum. So for the running sum for the third period would be 6 plus 7, 13. For the fourth period, it would be 13 plus negative 9, which would make it 4, and so on. So these are the running sum of forecasting errors. Ideally, the running sum should be close to 0. The absolute errors. Absolute errors are the positive values of errors, so we can calculate it very easily by saying it's equal to ABS, bracket open, and the error term. So we enter, that's the absolute error. We drag the formula. The advantage of absolute errors is sometimes very high positive and very high negative errors might cancel each other to give a very low bias, but they're still errors. So the negative value, effect of the negative value, is taken away here. And the mean absolute deviation is the average of these absolute errors. So this equals to average of all these values of absolute errors to give us absolute error of 6.166. So this is the MAD, or the mean absolute deviation. The percentage error is the MAD, okay, divided by the actual. That's what the percentage error. Now percentage error becomes very important because an error of say a 1 unit on a forecast of 100 unit is a 1% error, but an error of 1 unit on 10 units is a 10% error. So error cannot be absolute, it has to be a percentage, and that's why we use this percentage error. I sum up, or I drag the formula to get the percentage errors, so 0.015 or 1.5% in the first period, 5.6% in the second period. The average of all these percentage errors is the MAPE, or the mean absolute percentage error, so equal to average of all these numbers here to give me the mean absolute percentage error. So MAPE is the average of the percentage errors. Let me write those things again so we know what we're talking about. The bias is the average of the errors. The MAD, or the mean absolute deviation, is the average of absolute errors, and the MAPE, or the mean absolute percentage errors, is the average of the percentage errors. Now tracking signal is the last. Now to find tracking signal, we first need to find the cumulative absolute errors. So here it would be 2. In the next period it equal 2 plus 8, so it's 10, and so on. Next period will be 10 plus 7, 17. Let's drag the formula to make it easier for us. Now the running sum, or the bias, the MAD, are calculated at the end of a given period. Tracking signal exists for each and every period. So the tracking signal, the formula is the running sum of forecast errors, which is the column E, divided by MAD up till that point. So here it would be the running sum of forecast errors, which is this, divided by MAD. So MAD would be the cumulative absolute error divided by the period. So it's 1. We'll use the serial number here to help us make the formula easier and drag. So it's minus 1, because it's minus 2 divided by 2. 2 divided by 1 is the MAD at this point, and I can drag the formula here to get a tracking signal at various points. So some firms set up quality control policies that tracking signal should not go above a certain value. Wonderful. So what we have learned is 4 basic simple methods of measuring forecasting accuracy: the bias, which is the average of the errors; the MAD, which is the average of the absolute errors; the percentage error mean is the MAPE, mean absolute percent errors; and the tracking signal, which is calculated for each and every period, which is the running sum of forecasting error divided by MAD. Thank you for watching. I hope you liked the video. Please like it if.
Okay, so that's the end of Piyush. We got one more here on regression, and this is a new woman. I don't remember what her name is.
Hundreds of records to update. How on earth are you going to do that?
Well, I have
One by one, of course.
Linear regression is easy to do with Excel's built-in tools. In this video, we'll explore what linear regression is, why it's useful, and the Excel tools that enable you to do it with a click of just a few buttons. Let's start with an example.
Here I have some data on plant growth, how many hours sunlight it gets per day, and how much rain in millimeters. One way I can understand how sunlight and rain contribute to growth is to use linear regression to model the relationship between the dependent variable, in this case the plant growth, and one or more independent variables. Here we have sunlight hours and rain.
It's useful because it allows us to identify the relationship between two variables and make predictions based on that relationship. It's commonly used in fields such as finance, economics, and science to make predictions and inform decision making.
To model linear regression with Excel, I need to organize the data into a table. We're going to start with just one independent variable. Here I've got sunlight, and this way we can use charts to model linear regression. I want my independent variable in the first column and then the dependent variable in the next column so that they're plotted on the X and Y axes respectively. So with my data selected, I'm just going to insert, and I want a scatter chart. Let's bring it over closer. And then I can simply add a trend line, and I'm going to just go into more options. Let's bring the formatting pane over here closer to the chart. You can see it's defaulted to a linear trend line. And down here I can choose to also display the equation and the R² value. Let's just bring them up here so they're not covered up by the grid lines.
If you're already familiar with these concepts, you can skip ahead to the next section where I show you how to use the free Analysis Toolpack add-in to perform regression analysis. You'll find timestamps in the video description. Otherwise, continue watching for an overview of how you can use the equation and R² value.
The equation y equals 0.08x plus 0.1667 represents a straight line that shows the relationship between the two variables. Relating it to this data, the equation can be used to predict or forecast the growth rate for a given value of sunlight. The coefficient, 0.08, is the slope of the line, which represents the rate at which the growth changes for every unit increase in sunlight. In this case, the slope indicates that for every 1 hour increase in sunlight, that is x, the plant growth in centimeters, which is y, is expected to increase by 0.08 centimeters. The intercept of 0.1667 represents the value of y when x is equal to 0. In other words, is the value of y when there's no x effect. In this case, the intercept indicates that the growth is expected to be 0.1667 when sunlight hours are equal to 0. Now, whether that's biologically true for plants, I can't say. Now, to use this equation to make predictions, you would simply substitute the value of x into the equation. So 0.08 times, let's say we have 5 sunlight hours, plus 0.1667 gives us a growth of 0.5667 centimeters. By the way, we can also generate the equation using the linest function. So the known y's are the plant growth, the known x's are the sunlight hours, and that gives us the same slope, coefficient, and intercept that we have on the chart.
The R² value, also known as the coefficient of determination, is a statistical measure that explains the strength of the relationship of a linear regression model. It's a number between 0 and 1, where 0 indicates that the model does not fit the data at all. 1 indicates that the model perfectly fits the data.
To put it simply, here we can say 52.5% of the plant's growth is a result of the sunlight hours. A high R² value indicates that the independent variables have a strong relationship with the dependent variable and are able to explain a large proportion of its variation.
We can also perform regression analysis with the Data Analysis Toolpack, which can handle multiple independent variables. For example, we could model the effect of sunlight and rain on plant growth.
The Data Analysis Toolpack is a free add-in available in Excel. You can enable it via the File tab and then Options, and then down in Add-ins, I want to then click Go, and here make sure it's checked in the box and click OK. You'll then be able to access it on the Data tab of the ribbon on the far right, Data Analysis. Here I want to choose Regression and click OK. Now it remembers my selections from earlier, but let's just delete them and we'll start from scratch. So my input range is y, that's my dependent variable, in this case growth. And my independent variables are sunlight hours and rain. These variables need to be in columns that are adjacent to one another so you can select them in a single range. I've got labels checked because I've selected the row labels for my columns. And I'm just going to pop it here beside the data. I've also got residuals checked and residual plots. Let's click OK and take a look at what it gives us. Now there's a lot of information here, so I'm going to just cover the key results. The regression statistics measure the strength of the relationship between the variables. R values close to 1 show a strong positive relationship, and R values close to -1 show a strong negative relationship. R values close to 0 show no relationship at all. And we can see from this data that the relationship between the variables is strong. The R-squared value tells us that 94.6% of the growth is as a result of sunlight hours and rain. The standard error tells us how wrong the model is on average. The lower value, the better. In this example, we know that the standard distance between the predicted growth and the actual growth is on average 0.06 centimeters bigger or smaller. The analysis of variance table, ANOVA for short, measures the levels of variability within your model. The coefficients table returns a series of statistical tests. Here we can see that both sunlight hours and rain have a positive association with growth, and that for every sunlight hour the plant will grow 0.066 centimeters, and for every 1 millimeter of water it will grow 0.038 centimeters. Now the residuals shows the difference between the actual data points and the predicted data points based on the equation. We know from the chart that in this example the equation is y equals 0.08x plus 0.1667. They illustrate how well your model fits the data. Now ideally the residuals should be scattered around 0. And because I chose to plot them, we've got these two charts here that allows us to visualize them. And we can see that they're all within 0.1 plus or minus.
I hope you found this tutorial useful. You can download the Excel file containing the examples for this lesson from the link here.
Well, you don't need to because I've already downloaded it for you. So I will put this in the chat, but here's all her data. And you can go through it to your heart's content. There's also some, if you want more work on seasonal indices and seasonality and trend, and more seasonality and trend, there's a bunch of YouTube stuff in here. Again, they're going to ask you general questions about this stuff. Nah, they probably won't have you doing the math. Any questions? If not, we will do questions for the next 2 days. Talk to you guys tomorrow.